In this example, we're told we have an incompressible viscous fluid that's flowing past a solid flat plate down here, which has a depth b into the page. And the flow initially has some uniform velocity called u infinity. So it's coming in uniform. When it hits the plate, we have the no-slip boundary condition that gives you a zero velocity at the plate surface. And then far away from the plate, we still have the u infinity velocity way out here. So there's some transition between zero velocity and u infinity. And that velocity profile is being approximated here as a parabolic shape, given here, where y is the distance from the surface of the plate upward, and delta is where you are roughly to where it's equal to u infinity here from the parabolic profile, very close to where it's u infinity. Or actually here, it's actually equal to u infinity, I should say. And this kind of flow situation that's shown here is a classic boundary layer kind of flow scenario, something that we'll touch on later in the course. A boundary layer is a thin layer of fluid adjacent to a solid boundary where you get a lot of the, well, you get essentially all of the shear stress occurring in the fluid. Remember, the shear stress is just related to the velocity gradient, or the change in the velocity with respect to the change in position. So all of the velocity gradient, and thus all of the shear stress, is occurring in this boundary layer. Out here, outside of the boundary layer, the velocity doesn't change very much with position. In fact, here it's modeled as not changing at all, so there are no shear stresses outside. So this little dashed line is the region separating this outer inviscid flow, where there are no shear stresses, with an inner viscous flow, where all the shear stresses are. So this inner region is called the boundary layer. And again, it's a topic we'll cover later in the course. If you sketched out what a streamline looked like, it would actually be displaced outward just from conservation of mass. As the flow comes in here, the streamline, you can see it deflects outward somewhat. And the reason for that is because the mass flow rate here is larger than the mass flow rate here, because the velocities here are smaller than the velocities here. And so in order to have the same mass flow rate, the streamlines have to actually shift outward a little bit. So in this problem, we're asked to find what the height is h coming in, such that you end up with the height delta here going out. So the streamline starts at a height h, and then, as I mentioned, it's shifted outward. So at some distance x down the plate, how far does the streamline shift outward? That's the delta. So that's what we're asked to find first. Secondly, we're asked to find the force the plate exerts on the fluid over the distance x. So what we're talking about there is what kind of force does the plate exert on the fluid. And the reason we know some force occurs is because the fluid comes in with some momentum and it's going out with a different momentum. The momentum has changed because the velocity profile has changed. And we know from Newton's second law that if the momentum changes, then there must be some force that acted on the fluid. And that's what part B is, or part 2 is what is that force that's caused this velocity profile change. All right, so we're going to solve those two different situations here. Let's start with the first one, finding the upstream height that corresponds to the downstream height delta. This will be a conservation of mass kind of problem. And the reason I know this is because we're coming in with a certain amount of mass flow rate here, and we're going out with the same mass flow rate, assuming that it's steady. So there's no mass accumulation on the inside. So whatever the mass flow rate is coming in here, it has to be the same mass flow rate going out there, right? And since I've sketched a streamline here, we know that there's no flow across a streamline. So whatever mass flow rate comes in here, because we have a streamline on the top and a solid flat plate on the bottom, whatever mass flow rate comes in here has to be the same mass flow rate that goes out. So let's start with conservation of mass then. So we'll write it out, and we'll show our control volume as well in just a moment. So just a reminder what the terms mean. This first term is the time rate of change of mass inside the control volume. And then this is the mass flow rate out of the control volume through the control surface. So we are going to apply conservation of mass to a control volume. So the control volume I'm going to choose here is one that cuts across the inlet stream, cuts across the outlet stream, because those are important because I'm trying to relate H and delta, so that's why I'm drawing the control volumes cutting across right at those locations. I'll cut across right at the bottom, so there's no flow out of that boundary, and then for this particular case, I'll draw my upper part of the control volume to follow the streamline, so there's no flow out through the top. So I'm going to apply conservation of mass to that particular control volume. So I'm assuming it's a two-dimensional flow. There's no flow in or out of the page. I'll assume that the flow is steady so that this first term is 0. And when I set something to 0, I like to indicate why it's 0. So it's 0 because it's steady. What I mean is that when I say steady, nothing is changing with time. If I look at this problem right now and I see what the velocity profiles look like, and then I look at the same problem an hour later, it'll still be the same velocity profiles. It doesn't change with time. So any ddt terms will become 0 because it's steady. So again, I think it's a good way to communicate what you're doing by saying it's 0 and explaining why. Okay. Now the next term is the mass flow rate term. So we have two places where there's mass flow rate in or out of the control volume. We have it over here on the right-hand side where it's going out, and then we have it coming in on the left-hand side. So let's do the left-hand side first. So over there we have the density. We're going to assume that we're dealing with an incompressible flow. The relative velocity will be the velocity of the fluid. So we have a part of a coordinate system here. We have the y direction headed upward here. Let's put x headed downstream. Well, I guess we all actually already have it down here. So our velocity of the fluid will just be u infinity I hat. The control surface isn't moving, so the relative velocity is just the velocity of the fluid. And then the area vector there, well, the outward pointing normal vector is pointing upstream. So the area vector there will be h times the depth in and out of the page, which we said was b, and in the minus I hat direction. Give myself a little more space. So that's what we have at the inlet. Again, just to recap, that's our velocity coming in. It's just u infinity. This is our area coming in. H is this height, because that's the height at the start of the streamline. B is the distance in and out of the page. And the minus I hat is because my outward pointing normal vector is in the minus x direction. And I don't have to worry about doing any integration here at the inlet because it's a uniform velocity profile. So I don't have any change in the density or the velocity over that surface. Okay, so that's the inlet. Let's now do the outlet. Now here, you can see clearly that the velocity is changing with respect to height. So here I'm going to have to actually do an integral. So let's write this out. So we have integral of the density. The velocity there, well, of course it changes, but over a small little height difference here, call it dy, over that small differential height, the velocity is well defined. So I'm going to do everything in terms of little bits of area. So the velocity over that little area will be the u infinity times 2y over delta minus y over delta squared. And that's in the I hat direction. It's in the positive x direction. You can see that here it's pointed to the right, and that's in the positive x direction. And then the area vector there is going to be the dy times b and that's going to be also in the positive I hat direction. The outward pointing normal vector there, I'll draw it up here, n hat, is pointing in the positive x direction. So that's a positive I hat. And then I'm going to integrate as y goes from 0 out to delta, because I'm going from the bottom of the plate up to where the streamline is, which is a distance delta. Okay, so again, just to recap, I have to integrate because the velocity profile is changing over a little area, dy times b, this is what the velocity is there. And it's in the positive I-hat direction, and the area is also in the positive I-hat direction. And I'm integrating from 0 to delta because that's going up to the top of my control volume. All right, so let's go ahead and simplify this then. We can evaluate the first dot product, so we'll have a rho u infinity h times b, and then there'll be a minus there. Because of the dot product, there's the minus here. And then the next term will be the integral from 0 to delta of rho u infinity 2y over delta minus y over delta squared times b times dy. And all that equals 0. So we can go ahead and solve for this. You can see there's some terms that drop out, like the rho and the u infinity. Those will cancel out. Same sort of thing with the b. That'll divide out. And then we can solve for h in terms of delta. So I'm not going to work through the integration here. It's actually not a hard integration since it's a polynomial. I'll just give you the final result once you simplify everything down. Ultimately, you'll get h is equal to 2/3 delta when all is said and done. Okay, so all I did to go from this step down to this step is just evaluate the integral and simplify. So now we know how the incoming height is related to the outgoing height just from conservation of mass. Hopefully that part seems straightforward. Let's go on to the second part, part 2. For that part, we're asked to find the force. Now, when I think about this, if I'm going to try to evaluate a force, and I know that that force is caused by changing linear momentum, that makes me immediately think of the linear momentum equation, that I should be applying the linear momentum equation specifically in the x direction, since it's the force in the x direction, and the linear momentum changes are occurring in the x direction. So I'm going to apply the linear momentum equation in the x direction to that same control volume. It's very common when you apply the linear momentum equation to also have to apply conservation of mass. So it's not unusual to also use conservation of mass in linear momentum problems. So I'll go ahead and write down, I'm using the linear momentum equation in the x direction. We'll write down what the equation looks like. Your goal is to work enough problems so that when you write down the linear momentum equation in conservation of mass, you don't have to look them up in a formula sheet. They should just come naturally. If you're still looking it up in a formula sheet, then you haven't done the problem. You haven't done enough example problems on your own. Okay, so let me just talk about the various terms in the linear momentum equation. So this first term, within the integral, that's the linear momentum inside the control volume in the x direction, since it's the x component of the velocity. So that's the linear momentum within the control volume. So this is the time rate of change of linear momentum within the control volume. This next term is the flux of linear momentum out of the control volume through the control surface. So as fluid comes in and out of the control volume, it carries in its own linear momentum and then takes its own linear momentum out. And so that's what this term represents. The term in parentheses is the mass flow rate. That's just the dm dot. A little bit of mass flow rate. So mass flow rate times the velocity gives you the flow rate of linear momentum. And then here, of course, we have our body forces in the x direction and surface forces in the x direction. So let's evaluate all of those terms for our control volume. So we have our control volume already, and we have our coordinate system. So the first term will be 0 because, again, it's a steady flow. We're saying that nothing's changing with time, so the linear momentum within the control volume is not changing with time. Let me do the force terms next. Body forces in the x direction. We'll say that's 0 because we'll say that gravity's acting at best, acting downward. So So we don't have any body forces in the x direction. Now for surface forces, there we do have something. So let's go back up to the picture. The surface forces that we would have might include pressure and viscous forces and resultant forces, that sort of thing. Well, we're not told anything, I don't think we're told anything about what the pressure is in this profile. We're going to assume that the pressure everywhere is uniform, that pressure everywhere is atmospheric pressure. In that case, if we do it in terms of gauge pressure, there's zero pressure force here, zero pressure force here, and because this is inclined, there'd be a projected area in the x direction because this is lower than that. But since it's gauge pressure of zero, there is zero pressure force in the x direction on the top surface as well. So there are no pressure forces acting on the surface. Now, as far as viscous forces in the x direction, well, the vertical parts, there are no horizontal components of viscous forces there, so you don't have to worry about that. Along the top, because that streamline or because the dashed line here represents the transition from where you have no velocity gradient to within that little dashed line you do have velocity gradients. Since our streamline is outside of that, or the top of our control volume is outside of that, the velocity gradient along that dashed line is zero, right? You can see here there is no velocity gradient, and right up here, right at the very edge, there's no velocity gradient right at the edge. So there are no viscous stresses on the top. Remember again that the viscous stresses are like mu times du dy. So if du dy is equal to 0, then tau has to be 0. And the du dy right along the top of our control volume is 0 everywhere because it's a uniform velocity outside of our boundary layer. So we don't have to worry about shear stresses on the top. And as far as on the bottom, there definitely are shear stresses on the bottom, but we've lumped them all together to give us this force. This force here is the resultant force due to those shear stresses on the bottom. So the only surface force we have to worry about is this F, and that's in the minus x direction. So let's put that in. So that's minus F. Again, that F represents the resultant force from all the viscous stresses acting on the plate at the bottom. Okay, now the last term that we have to evaluate is the linear momentum flux term. So let's evaluate that at the left side first, and then we'll do it on the right side. So on the left side, we'll just write out each term separately. We have the x velocity. Well, that x velocity on the left side is just equal to u infinity, and that's positive u infinity because it's in the positive x direction. And then we have the mass flow rate term, which we've already evaluated right up here. Remember from conservation of mass, we already evaluated that term. So I'll just copy it down again. So that'll be a minus rho u infinity h times b. So let me highlight. The yellow here is this term. And then the green, let me do this in a darker green. This green is this term. Okay? And we don't have to do the integral here because everything is uniform right at the inlet. Okay, now let's focus on the outlet. So there, the x velocity there, remember the velocity is changing, so here we do have to actually do the integral. So I'll do it in terms of little areas. So over this little area, dy times b, the velocity there is given by this parabola, so I'll write that down. And that's also in the positive x direction. So this will be the, if I can remember the profile, u infinity times y over delta, or it's 2y over delta, minus y over delta squared. Let me change my bracket here. So that's my yellow velocity here. It's the velocity u sub x. It's this velocity right here. It's that one. And then here's our mass flow rate term, which we, again, previously evaluated for conservation of mass right up here. So I'll just copy that down again. So that's a rho u infinity 2y over delta minus y over delta squared times dy times b. And then that I'll highlight in green because that's my mass flow rate term given right here. So that's what's occurring at the outlet, and I have to, of course, integrate that because the velocity profile is changing, so I should put my integral here as y goes from 0 to delta. And you can see here it's the y that's changing, dy, so my limits are y goes from 0 to delta. All right, that's everything that we need to set up this problem. So we can now evaluate it and solve for the force. As we do that, one of the things you'll see is there's an h here, but we solve for h in terms of delta there, so we can substitute this right in there to help us put everything in terms of delta. I'm not going to go through the mechanics of evaluating this integral. This one's a little more complicated because you have to multiply through these polynomials, and it's just tedious, but it's calculus that you've done before. It's nothing too particularly difficult, just tedious. When all is said and done, you'll get that the force comes out to be 2/15 rho u infinity squared b times delta. So that's what you'll get when all is said and done. So the force acting on the plate is related to not only the upstream conditions, the u infinity, but it's related to the thickness of the boundary layers. Basically, this force is related to how much we've modified the boundary layer profile. Delta is this thickness. So the larger the force corresponds to a larger delta. We've modified more of the velocity profile. It's this kind of, you might expect that from Newton's second law. The larger the change in the linear momentum, the larger the force will be. Okay, so hopefully that part of the problem makes sense to you as well. Well, it turns out we can also use a different control volume to solve this problem. So I'm going to rework it the second way. So this first control volume I used actually followed the contour of that streamline. Let me do a different approach. I'm going to erase that control volume, specifically just erase the top of it. And let me use a different control volume now. Let's use one that's actually just a rectangle. Okay, so this one's rectangular, so that the height over here is delta. Okay, so now let's solve the problem this way. We should get the same answer because we know that our results shouldn't depend on what the control volume looks like, right? So, okay, let's do conservation of mass first of all. One of the things I should point out with conservation of mass is we have the flow coming in here, going out there, but now we'll actually have flow going out through the top. That if I chose a streamline that was a little bit different, let's say if I had a streamline that started here, you can see that there's actually, that streamline would deflect outward. So we would actually get some flow going out through the top of the control volume. Right, so in this particular control volume, let's see if I can erase that. The top of the control volume does not follow a streamline, it's just horizontal. So we can have some flow out through the top. So I'm going to call it m dot top for the mass flow rate going out through the top. So we need to account for that both in conservation of mass and linear momentum. So let's evaluate conservation of mass for this new control volume. We'll rewrite the equation and then simplify. Always start with your governing equation. All right, so first term again is going to be 0 because it's steady. The second term, if we think about the left-hand side, that'll be a density times u infinity in the I hat direction. Dot product with, in this case, it'll be a minus delta times b I hat. Okay, so let's go back up. Just keep in mind minus delta B times I hat. The minus I hat comes from the normal vector pointing in the minus x direction. The B, of course, is in and out of the page. And here, now our height is delta. It's no longer h because I'm making the top of this horizontal, so it'll have the same height as the right-hand side. So that's what we have coming in from the right-hand side. Now, coming in from the left-hand side. Going out at the right-hand side will look exactly the same as what we had before because nothing's really different from the right-hand side. So we'll just recopy that. So that is what's happening on the right-hand side, if I've done all that correctly. So it's, again, this is exactly the same as what we did up here. Okay. And then there's one last term now, the mass flow rate going out through the top. Remember, because of our choice of control volume here, straight across the top, we know that there's actually some mass flow rate going out through the top because we know that the streamlines bend upward. So if I started with the streamline just a little above the one that's shown here, I know it's going to go out through the top. So there is some mass flow rate going out through the top. So I've accounted for that here. So we can go ahead and solve for our, kind of rearrange this and solve. And I'm going to solve for m dot top here. I want to find the mass flow rate out through the top. What I'm ultimately trying to do in this part of the problem is solve for the force. So I'm going to use conservation of mass and linear momentum again. So you'll see where the m dot top shows up in linear momentum. So if you solve for m dot top from conservation of mass, it comes out to be 1/3 rho u infinity times delta times b. Okay, so that's what you get from conservation of mass. Again, I'm not going to go through all the tedious details of evaluating the integral. Now let's do the linear momentum equation in the x direction on that same control volume. So we write out the linear momentum equation. Again, you want to get to the point where you can do this without having to look it up. My coordinate system, I probably should have said this earlier, the coordinate system I'm using to evaluate my linear momentum equation is a fixed coordinate system that, if you look back up at the picture here, it's just fixed in space, so it's inertial. So the form of the linear momentum equation I'm using is just kind of the standard one. All right, now to evaluate the linear momentum equation, first term is 0 again because it's steady. Our surface force in the x direction, this will still be just minus F. There, again, let me go back up to the picture. We have our minus F here. There's no pressure force anywhere on the surface here because we said that it was just atmospheric or 0 gauge pressure. There are no viscous forces along the top because the velocity gradient out here on the top is 0. So if the velocity gradient is 0, the shear stress is 0. So that's our only surface force is the F in the minus x direction. And then there are no body forces in the x direction. We've already talked about that. So now we just have to deal with the x linear momentum flux out of the control volume. So on the left-hand side, we've sort of worked this before. This will be a u infinity for the ux velocity. I'll highlight that again. Then we have then the mass flow rate term, which we just evaluated a little bit ago. That'll be a rho minus rho u infinity delta times b. That's the green one. We arrived at that from up here. Remember that the height of our inlet now in our new control volume is delta. Okay, then going out through the right, that linear momentum flux will be, we've already evaluated that in the first part of the problem, so I'm just going to write out the whole thing. So this term that I've just written down is the yellow ux velocity right up here. And then we have our mass flow rate term, which we've evaluated before. So that term, hopefully I've written it all correctly, is our mass flow rate term. And again, we've already solved for this one previously. That was the same as what we have right up here. Okay. And then we actually have one more linear momentum term, and that is out through the very top. Because we have some mass flow rate out, that mass flow rate out is not going vertically. I tried to actually kind of give you a hint about that when I drew it at an angle. You can see that the velocity right along this top is u infinity everywhere, right? You can see here it's u infinity, out here it's u infinity. So going out through the top, the x component of the velocity out through the top is u infinity. So when we evaluate the linear momentum equation, this ux term will be our u infinity, right? Because that's the velocity, the horizontal component of the velocity going out through the top. And then the mass flow rate going out through the top, we already said, was just m dot top. So that's our green term here. Hopefully that makes sense. It's a little, you have to think about it just a moment. Let me go back to the picture. Again, we know that there's some mass flow rate going out through the top, but its horizontal component, everywhere along the top here, it's u infinity velocity. At least this is the horizontal component. I should probably put a ux equals. You know, everywhere on the top here, ux is equal to u infinity. There's a slight vertical component because there's some velocity going upwards, but we don't care about that vertical component in our x linear momentum equation. It's only the horizontal component we care about. So that's why we have the u infinity. It's in the positive x direction. Okay, so now we have everything we need. We can also substitute our m dot top down here and then solve our resulting integrals and solve the equation. And if you go through all that, what you'll get, as expected, if you do all your calculus and algebra correctly, it'll be the exact same result that we had previously. It'll be the same result as what we have up here. So there are two different ways you could have solved this problem. You know, your choice of control volume just depends on what you prefer. I think personally, for me, it's easier to understand the control volume that follows the streamline, like our first method that we did. That to me just just seems easier to me. But using this rectangular control volume works too. The tricky part about that is the m dot top. You have to recognize there's some mass flow rate out through the top, and the horizontal component of the velocity of that fluid going out through the top is u infinity. But hopefully the conservation of mass part of the problem makes sense. Hopefully the linear momentum part makes sense. My suggestion on working linear momentum and conservation of mass is just, you know, write out your equation and evaluate each term individually, step by step, right? Like I'm doing here, each term individually. And then when you do this term, this is the trickiest term, just do that individually as well. Write out your ux, write out your mass flow rate. Don't try to do too many steps in your head. If you do too many steps in your head, you're likely to make mistakes. So just write them out individually and then simplify it. It'll be, you'll make fewer mistakes for yourself, and then it's easier for other people to understand. Okay, we're going to go ahead and end the example there.